Hello everyone and welcome to Remote Thermodynamics for Mechanical Engineers. Today we're going to go through an example solving a Rankine cycle. So Rankine cycles are pretty important power generation cycles that work by boiling water and then running the steam through a turbine to generate mechanical power. A TS diagram for a cycle like this looks something like this, where we have our hot fluid that's coming into a turbine here, and then as it expands through the turbine, its temperature goes down, and if it's a real turbine, then its specific entropy goes up. And then what happens is we cool it back down so it's a liquid. We pump it back up to a higher pressure because that takes less power to pump up a liquid instead of a vapor, and then we heat it back up so that it can go back through the turbine again, and it's called a cycle because we do this over and over again. So we get power out from the turbine, heat is rejected in the condenser, we put power in at the pump, and then we add heat in the boiler. When we think about how to characterize this cycle, we think about thermal efficiency, where the desired energy effect is net power, or the power generated by the turbine minus the power consumed by the pumps, divided by the energy cost, which is the heat in, which in many Rankine cycles we generate by burning coal, or maybe by performing a nuclear reactant, or maybe by performing a nuclear reaction. If we're comparing the actual efficiency to some ideal efficiency, the ideal efficiency is not 1, but the Carnot cycle efficiency, where we take 1 minus T hot divided by T cold. And because those temperatures aren't temperature differences, we have to be sure to use an absolute temperature, so something like Kelvin scale or Rankine scale, if we're using imperial measurements, to get the right answer for the Carnot efficiency. Another way that we can characterize a heat engine is with the backwork ratio. So the backwork ratio is trying to ask how much of the power in the system, so the backwork ratio tries to tell us what fraction of the power that we're generating from, in this case, our turbines, goes in to powering the pumps. So we would like to have a high efficiency but a low backwork ratio. So when we go through each of these components, basically we're going to treat this problem like Lego and analyze each separate component inside our thermodynamic cycle. So for each one of those components, we can do a first law analysis. So in a first law analysis, we'll start with this open version of the first law because mass is flowing through each of these components. We'll typically assume that the system is at steady state, that there's one inlet and one outlet into these components, that the change in kinetic energy can be neglected, like the change in potential energy. We'll assume for each component that it's either adiabatic, meaning that it's insulated and not losing heat, or that it's passive, meaning that it's not generating or consuming power, that there are no friction losses in the system, and there's no heat losses as the fluid is moving through whatever plumbing is connecting our different components. When we do that, we get some equations that we'll typically see in this type of analysis. We'll see that the turbines are going to be equal to the power generated by the turbines, or the power consumed by the pumps is going to be the mass flow rate times the specific enthalpy into the component minus the specific enthalpy out of the component. I'm always going to get this from the first law. So when I'm talking about turbines and pumps, I'm going to keep H in minus H out, and I'll let the sign tell me if I'm producing power, that's positive, or if I'm consuming power, that's negative. Similarly, for the heat exchange devices, I'll find that the heat is equal to the mass flow rate times H out minus H in, and again, I'll let the sign of my Q dot term tell me whether I'm adding heat or losing it. Here, we're going to find our enthalpies using methods described earlier in our textbooks. right? So here we're typically talking about, for Rankine cycles, we'll typically talk about water as a working fluid. So as long as it's not a saturated liquid, then we'll use our tables. And if it is a saturated liquid, then we'll talk about how to find our differences in enthalpy as we work through our problem. If we have a real turbine or a real pump, we might be interested in the isentropic efficiency of those components. So turbines produce power, and they lose power in the real system. So the real system has losses, so it produces less power than the ideal system. So we can see that for a turbine, we'll put the real power divided by the ideal power, because our efficiencies always have to be less than 100%. If we're talking about pumps, we still have power divided by power, but in this case, a real pump will require more power than an ideal pump because it has to overcome the losses in the system. So in this case, if we're talking about an efficiency of a pump, we take the ideal power divided by the real power. So here's an example in what it might look like. So we have our 4 components in this sort of basic Rankine cycle. And then we also have some cooling water that's coming in and out of our condenser. So the heat that we're losing from our working fluid in the condenser is going into this cooling water. Now the problem gives us a lot of information that we'll start with. So I always want to draw a state table. And in this case, I have my states numbered. And then I have different properties that I feel like I will need on my table. The problem tells us that the turbine and pump efficiencies are 0.85, and we're asked to draw a TS diagram, find the thermal efficiency, find the mass flow rate of the cooling water, find the backwork ratio, and track any assumptions that we might make. So I'll start by looking at the Rankine cycle, which happens in states 1 to 4. So this is with our hot fluid. And then we'll talk about the cold fluid, which is states 5 and 6. So state 2s, I already know that the reason that this is, so this is as I go through my ideal turbine, and my ideal turbine has the same specific entropy at the outlet that it did at the inlet. So I know that my specific entropy stays the same as I move through the ideal turbine. And then I can look on my tables and I see that for that fluid with 95 degrees Celsius and a specific enthalpy of 6.87, I can go to the tables and find H. Here's what my Rankine cycle looks like as I draw my TS diagram. So as I move through the ideal turbine, I move from state 1 to state 2s. That's a vertical line, so the specific entropy stays the same. But then when I go through the real turbine, what happens is the specific entropy increases. So I move not to 2s, but to 2. The same is true when I move from 3 to 4s. That's a vertical line. And then when I move from 3 to the real pump exit, that's 4, then I'm moving to the right because the specific entropy is increasing. So here, I want to find the symbolic solution for my thermal efficiency. I take my net work, which is my energy benefit, divided by my heat that I'm adding at the boiler. So then I'm going to add my pump power that I get from doing a first law analysis to my turbine power. Notice the color coding that I've used here where the turbine power is in green and the pump power is in red. That's because I know the turbine power will be positive and the pump power will be negative. At this point, I don't know the thermal efficiency. I don't know the turbine power. I don't know the pump power. And I don't know how much heat I'm adding in the boiler. So it's nice that I have a symbolic solution. I just don't have any answers yet. So how do I use the first law to find the turbine power, the pump power, and the heat added in the boiler? I've talked about this already, but I'm going to do a first law analysis on all these different components, and I'll do it quickly right here. So the assumptions that I'll make are that the system is at steady state, that all of these components have one inlet and one outlet, that the change in kinetic energy is not important, and neither is the change in gravitational potential energy. For each of these components, I'll choose whether they're adiabatic or passive. I'll say that there's no friction losses in the lines and that there's no heat losses in the lines. And when I do that, I find that the turbine power is m dot times h in minus h out. The pump power is also m dot times h in minus h out. And the boiler is m dot times h out minus h in. So now I can take the symbolic solution that I had before and add these equations that give me a more specific definition of what those powers and heat additions are. Now, the nice thing about this particular Rankine cycle is that the mass flow rate doesn't split anywhere, so all the mass flow rates in this term will drop out because there's a mass flow rate that's a function of all the terms in the denominator and also all the terms in the numerator. So the mass flow rates drop out, and I'm left with this equation, H1 minus H2 plus H3 minus H4 divided by H1 minus H4. I know H1, I don't know H2, I know H3, I don't know H4, I know H1, and I don't know H4. So I have a symbolic solution, and I could get this answer if I could fix states 2 and 4. So now I have to try to find H2, and I can do that using the isentropic efficiency of the turbine. We've talked about this already, but the isentropic efficiency for turbines is real power divided by ideal power. When I add in my equations, I get this. Again, my mass flow rates drop out, and I'm left with this equation. I know the isentropic efficiency. I know H1, and I know H2S. So the only thing I don't know is H2. So I could rearrange this equation and find that H2 is 2,628 kilojoules per kilogram. This makes sense because H2 should be bigger than H2S because we can't get quite as much power out of the real turbine compared to the ideal turbine. I also want to find H4, and I'm going to use a similar process for that. But first, we need to find the outlet for the ideal pump. Now, for turbines, we just use the fact that the specific entropy does not change, but in this case, for pumps, because I'm moving between two states that are both subcooled liquids, I can use that delta H is equal to the specific volume multiplied by the change in the pressure. I do have to watch my units here. So if I look at my pressure, it's given in bars, right? So I know that a bar is 100 kilopascals. So I can cancel out the bars, and I get that this is 7.9 meters cubed per kilogram times kilonewtons divided by meters squared, which is not really the unit that I want. I want this in kilojoules per kilogram. But it turns out if I look at this, I get kilonewton meters per kilogram, and a newton meter is a joule. So this makes sense. This is also why when I write down my information on my state table, I like to keep pressure in kilopascals because my units work out as I do the calculations. Next, I'll use the isentropic efficiency for the pump. My mass flow rates drop out again. Again, I know the isentropic efficiency. I know the inlets, which are the same for both. I know the ideal outlet, but I don't know H4, the outlet of the real pump. But since it's the only thing I don't know in this equation, I could isolate for it and calculate what H4 is. Again, this is larger than H4S, which means that my real pump consumes more power. Delta H will be larger in the real pump than in the ideal pump. So now I can take my symbolic solution for thermal efficiency. I can plug in all my values of specific entropy, and I can find that the thermal efficiency is 28.4%. Now, the problem asks me to find the mass flow rate of the water moving through the cooling side of the heat exchanger. So what I need to do is a first law analysis on this heat exchanger here that I'm using to cool my working fluid. So this is my control volume, and I will do a first law analysis. So I'm going to say that the system here is steady state, that there's no change in kinetic energy, no change in potential energy. The system is both adiabatic and passive. Now, this is a little bit confusing sometimes because it's a heat exchanger. It is exchanging heat, But when we say that it's adiabatic, what we mean is all the heat that leaves the hot side of my heat exchanger goes into the cold side of my heat exchanger. Or another way to think about this is that none of the heat from my heat exchanger or from my hot fluid escapes to the environment. Again, I'm going to say that there's no friction or heat losses in my system. If I do this, I get this equation. I can see that the inlets, right? So I'm going to separate this by the different mass flow rates because I know that my mass flow rate is one value and my mass flow rate on the cold side is another. So here I can isolate for, well, I'll bring the cool side over to one side and the hot side over to the other. I can isolate for a cool mass flow rate, right? I guess what this line says is that this is what we expect. We expect that all the heat that goes into my cold side is coming out from my hot side. So this is good. It's a nice check. It makes sense, right? And now I can isolate for my cool side mass flow rate, which I like to leave as a hot side mass flow rate multiplied by a ratio of delta H's. Because then if my units are constant for my delta H's, I don't have to worry about unit conversion here. That stuff should all just drop out. And I find that the cool side mass flow rate is 198.1 kilograms per second, which is nice because it's positive, which means that the mass flow rate is going in the direction that I drew it in my figure. This is because the delta H, H2 minus H3, is a negative number. So a negative times a negative is, in fact, a positive. So now I want a symbolic solution for my backwork ratio. Backwork ratio, we said, is the power of the pump divided by the power of the turbine. We want this value to be low because sort of the first consumer of the power plant is the power plant, right? So we want the power plant to consume as little power as possible. So in this case, because the mass flow rates, again, are the same, I can just say that this is going to be delta H across the pump divided by delta H across the turbine. I take the absolute value of these things, and I find that my backwork ratio is about 1%. And that's one of the things that's good about Rankine cycles is they typically have very low backwork ratios because it doesn't take very much power to pump a liquid up to pressure. So now I was given all of this information. I have found all of my states. I found my thermal efficiency, the mass flow rate of the cooling water, and the backwork ratio. So that concludes this example on virtual thermodynamics. Thank you.